Okay, so we have a couple minutes for questions, so just keep your hands up until I knock you. Okay, Joe.
Okay. Thanks. That was really interesting, Matt. I think I missed something really important. It's probably more to do with my powers of concentration in your explanation. But when you were describing the generalized Bell locality, does that rule out superluminal signaling in and of itself? Or could I build something where there's a constraint on the box thing where I can send the signal through by doing these constraints? It seemed to me that you could do that.
It doesn't, and that's why I was... So you have to imagine that your operational theory doesn't have superluminal signaling, and what you're trying to do with these block universe ontological models is reproduce those correlations. And it's like, you know, it's basically, this framework is similar to, I don't know if you're familiar with the Helsinki model. That allows signaling, is that correct? I think it does allow.
I don't think it does.
Okay.
I think it does.
The basic idea is yes, we're not going to have
That's not what you're
a
after.
priori constraints that this allows signaling.
Okay.
And that's why I was talking at the beginning about, well, we have to have some story about how that's going to go.
Oh, right, so that's the line you're taking out of your original options, is that you put everything into one box. That out of your how we deal with Bell's
it's going to be very difficult to come up with a general framework for working causal theories that also rules out signaling in a natural way. So it has to be imposed by hand.
Okay.
Thank you.
Oh, thanks, Matt. That's fascinating. Just a small point about what looks like a disagreement between us about zigzags. You said you didn't like zigzag model. And I use the term zigzag in my talk, but we're talking about different things. By zigzag, I just mean a kind of a path of influence in space-time. I'm not buying at all into the idea that the electron kind of has a direction of precession in time and then turns around and goes the other way. No, of course I'm dealing with a block universe, so it just world like. But we're just looking at the paths in space-time on which these influences travel. That's all right.
Yeah. Okay.
Okay.
That was beautifully clear. Thanks, Matt. It seems to me there's an asymmetry in your definition of causal and retrocausal. I'm not sure, in the sense that your definition of causal is that the constraints are functions for each gate going that way, or whichever way it is for you.
Yeah.
But forwards in time, your circuits all have a direction of time, don't they? Whereas your definition of retrocausal is not that you have a gate which is a function going the other way.
Sure.
Right, so wouldn't it be more natural if you want to have complete kind of time symmetry?
Yeah.
If your motivation is to have something in which you have, causal meaning really causal influence going one way, and retrocausal meaning really causal influence going the other way, to have define retrocausality as there being a gate for which the constraint is
So
a function anyway.
So there's two things going on here. There's the mathematical formalism of your theory, and then there's the probabilities that it has for both the ontic states and the random variables. So what I think is that really a physical theory is just specified by the latter. The former, whether I write things down in terms of constraints or not, or some other way, the former is just a particular mathematical formalism for that theory. So really, the notions of whether things are causal, you could define whether something's causal in the sort of analogous way to this in terms of just the probabilities of the theory. So really, with the definition of causal that I gave, all I really wanted to do with that is to sort of explain what it meant for sort of mathematical formalism to look explicitly causal. So maybe I should have called that sort of explicitly mathematically causal. Really, this notion of implicit causality is supposed to be the notion that the theory really can be formulated as something propagating forwards in time.
Could you have explicitly mathematically retrocausal then?
Well, you could, yes. You would just talk about functions from from right to left instead of left to right.
But that has no interest. It's not
Well, I mean,
interesting.
I think we certainly know that we have theories which have good explicitly causal formalisms, and we're trying to investigate the possibility that there might be retrocausality as well. And if you're being time symmetric, I think it makes sense to imagine that you're going to have sort of a bit, not necessarily going to be able to disentangle the two. So, you know, a constraint is sort of a priori, it's neither causal nor retrocausal, it's just a constraint. And that may have a retrocausal effect on the probabilities or not.
Ken just wants to ask something.
So, Faye, I think that the key issue here is that when he's defining retrocausality, there's some retrocausality here, but there's also could be some forward causality as well. If you reverse that definition, you are stuck with models that are only retrocausal with no forward causality.
No, just for a gate. Just for a gate.
Yeah, well, if you define
Just
all the gates reversed.
Yes, it says,
No,
I
I'm
mean,
just
might
saying
have-
for a gate you could say that the model is retrocausal if there's a gate which is one gate.
Oh,
That
right.
there is retrocausality in this model if there's one gate.
The problem is that the constraints of the different gates interact with one another, and it might be that you might have some explicit retrocausality in one specific gate, but it might be that because of the other gates you've got in your theory, when you hook them up all together, you get something which doesn't have any retrocausality in this sense. So that kind of thing could happen, and it's kind of difficult to identify.
Yes, Andy, did you have a point on that?
Yes, I just want to understand this definition.
Yeah.
X is something that you can observe, and lambda is like a hidden variable that you cannot.
Yeah.
So if I just look at observed things, then they should not depend on
Yeah.
changing
So
F to H.
I said earlier that you wanted to build sort of no signaling on the operational level into your conditions. I didn't really explain how to do that, but that's. But the point is, when you imagine some sort of super observer who's, so imagine that Bob is changing F to H, and there's some sort of super observer Alice who sees everything in the backward light code. Now it could be that if she just looks at the lambdas, she can't signal, but it could be some other time when they get one specific outcome, then when there's the outcome, there's some signal sent in the lambdas, right? So it could be that not on every single run of the circuit do I get a signal, but you get a signal some sort of fraction of the time, and you want to call that retrocausality as well.
But is it the case that if you have some set of observations that are just X's,
Yeah.
and you may build a model, including X's and lambdas, that is retrocausal, but for the same set of X's, you can also build a model that is not retrocausal.
Of course, especially if you allow the model to be non-local, then you can do that, of course, you can always do that. You're only going to be able to prove retrocausality under some other set of assumptions, of course, because we never directly observe the lambdas. So the only way you can prove a theorem which ends up at retrocausality is to make some other assumptions, such as locality and your particular framework assumptions and whatever. So that you can prove, I think, in this framework, but you're never going to say, well, just because I have these correlations without any other assumptions, that obviously means there will obviously always be other kinds of theory, non-local ones, for instance.
John, did you have a thing?
Yeah, okay, let's try. Well, so the theories I guess would be interested in simulating with this kind of model, like quantum theory, would be ones that are causal at the operational level.
Yeah.
And there's this neat result from Chiribella and others that's sort of equivalent to those signalings, or
Yeah.
applies no signaling anyway. Okay, so one thing one could do is put that in by hand,
Yeah.
just with a sort of suitable distribution over lambdas, retrocausal model that reproduces operational causality. But at the beginning you hinted something else. You said something about causality being emergent and ultimately reducible to something to do with thermodynamics.
Yeah.
So have you tried to marry that idea at all with
Well,
this?
I think that first of all I need to come up with a theory, and this hasn't been done yet. We need to come up with a theory in this framework that reproduces just all the quantum predictions. And then I'm going to want to think of that as, I mean, maybe I'm thinking maybe along similar lines to Valentini here. I'm thinking that state of affairs is going to be some sort of equilibrium state, and then I need to put in some. I mean, that's one possibility. Another possibility could be that once I've got that theory, I write down a slightly more general theory, which doesn't have the no signaling constraints, and then by imposing particular boundary conditions, I end up with getting rid of the signaling ability. I don't know. It is a bit vague and speculative at the moment. I wouldn't dispute that.
There's sort of 4 hands to go within so any of the 4 sensible. Yeah. These are sensible. So I've still got a Ray.
I just had a quick question about would it come out as local according to a definition? I think it has more of a global constraint than separate.
So I haven't.
Parity on the
There are certainly certain kinds of toy model that appears in the literature which definitely aren't in this framework. The Helsinki model, it does have constraints which are, like if you think of the sort of individual three-legged things as gates, then that's not local in the sense I've defined here. But I think that you can actually sort of redefine the terms of the model. So I haven't actually done this in detail, but if you were to sort of group up these into gates which consist of larger numbers of these things, or if you were to maybe transform to the sort of dual graph, well, I think that you could, something like that, you could transform that into a model that's local in this sense. So I don't think there's going to be a big problem there, but I haven't sat down and tried to figure out how to fit that in exactly.
Can you clarify a little more? We have this concept, modules and theories. We have GRW, Everett, Bohm, these are theories. And then we have some models, which sometimes less than models, like Speckens.
Yeah.
And in your case, model is kind of a general thing. And then you also have constraint models, which are supposed to be deterministic models, but your framework uses probability everywhere. Do you think that this language, so first the model is more than a theory and less than a theory, and why do you think that stating things in this probability language will be helpful to dealing with deterministic models, which sounds completely wrong tools to analyze?
Yeah. So first of all, constraint models are not deterministic models. What I mean is that if you impose the additional causality assumption, then they reduce the deterministic model in that case. They're not deterministic because basically because you just have a set of constraints, and a set of constraints may underdetermine things.
So Bohm and Everett are not here.
Okay, so the reason Everett's not here is, well, Everett sort of is here because but when I introduce the separability assumption, Everett doesn't satisfy that. Because the global quantum state, this Fletcher-Arontic state, doesn't satisfy, it's not a local beable, right? So it's included in the general framework, but not in that specific assumption. But so Bohm similarly, I would need to, so I can sort of weaken the separability assumption, but well, I suppose okay. So I should clarify. Everett isn't really in this framework because this is a single world framework. Okay. So measurement outcomes, these classical random variables, they have definite values. So let's forget about that. Bohm, I think you could put in this framework, but it would be a non-separable theory, and it would be a non-local theory, as you'd expect it to be. Just because you can, reduce this framework to the standard. It's a standard ontological models framework, and to the extent when you impose its causality, you reduce the standard ontological models framework. And to the extent to which you can formulate Bohmian mechanics as one of those theories, which you can, I mean the details are a little bit non-trivial, but you can do it. It's also going to be included here.
Can you tweak Bohm so that it becomes separable and retrocausal in your thing?
Probably. I mean, you can certainly, you can make any theory separable just by taking any of the non-localized vehicles and replicating them at every point in space-time. Now, that might mean that that the dynamics of the theory has to change in some way. You know, you're now going to have to reproduce the global dynamics of each local spot. Can you make it look retrocausal instead of looking more local? I don't really know. I think people have done things along those lines.
Southern locus.
Right.
I was just wondering if you could say a little bit about why you think the block universe has anything to do with causality or retrocausality.
I mean, it doesn't. So constraint. The idea of a constraint model doesn't have a priori notion of causality. Where causality comes in is with the idea that I've got some kind of free choice that I can choose between F and H. So once you make that assumption, then you can define what you mean by causal or retrocausal. But you don't really have to cash that out in terms of causality if you don't want to. Instead of saying that this is a free choice of the experimenter, you could just as well say that there's sort of many repetitions of a similar experiment that happened in space-time somewhere. A whole bunch of them happen to be describable by a circuit like this, another bunch happen to be describable by a circuit like that, and this is, you can say, well, this is about the pattern of correlations you get instead if you want.
But if you were to talk in terms of causality, why would there be any connection to the idea of the block universe?
Okay, so the idea is that in the block universe, you don't privilege either. It's really sort of a time symmetry requirement. So within the block universe, I'm not going to privilege, the idea that there's things propagating in any particular direction. Okay, so that means that I need a more generalized formalism of my theories. And then when I take that more generalized formalism and then say, okay, there are some parameters here which I'm going to talk about as being under the control of an experimenter, then you can see what notion of causality comes out. And then it's just going to turn out that sometimes you'll have things which are apparently causal and sometimes you'll have things that are apparently retrocausal. I don't know if I've really answered your question, but...
Thanks.
Just related to this, I'm just wondering if there's a feature of your formalism which is kind of making it hard to think about the question as to why in the ordinary cases we have forward causality rather than retrocausality. One of the things that I took the discussion of these sort of time-lapse depolarizer models to show is that things become symmetric once you take away the ordinary control that we have of the inputs. Mm-hmm. But in the quantum case, there's still causality because but in your model, to represent that, you'd need something which was like a random variable, the kind of thing we have at the output end, but which was operating at the input end.
Well, we do have those, though. Those are the preparation. So
but what is that? I mean, you choose, maybe I'm missing something, but you choose the preparation.
Yeah, so I did think about exactly how to present this, right, because there are various ways you could represent quantum theory in this formalism. So one thing is you could demand that when you have a preparation gate, that when you have an ensemble preparation gate, you could demand that the ensemble average is always the same state, or maximum mixed state or something. Then you could say that how I represent preparing another state has to be conditioning on that variable. So then things will become more symmetric, and in the generalized operational framework, this would be analogous to imposing sort of non-signaling conditions in both directions. You also have the option of making things more symmetric by explicitly allowing post-selection, but then that makes the kinds of definitions of retrocausality that I'm looking wrong. So you can make it time symmetric, but remember, I didn't need to say very much about the constraints at the operational level. I just said you should impose causality constraints. Well, you can impose some additional causality constraints to represent this kind of thing you're talking about as well. But it's not all that relevant for the basic construction of the ontological. But you can certainly imagine that you have a completely time-symmetric operational theory as well, if you want.
And Jeremy?
Let's go coffee.
Okay, and on that note, yeah, let's go to a slightly shorter than advertised, taking you back here at 10:40. So let's thank the speaker.